Ventali? Okay. So Daniel will talk about how to push the performance and the usability of ZKP using Plonky3 and Valida. Thanks.
Thanks so much. Yeah, so if any of you were at my other talk yesterday afternoon, that was going to be a little bit more of an introduction and high level, and today we can jump into some of the design decisions a little bit more closely. So I'm talking about the Valida VM, which we built on top of Plonky3. I'm here from the Lita Foundation, I guess I should say that. So we'll be talking about some high-level like categorizations, what does it mean to be a ZK VM, some of the limitations we've seen with other VMs out there, and then what we have done to build what we think is the fastest VM around, and maybe a little bit about the future. So a VM needs to be a ZK circuit that is universal, so it can prove succinctly and in zero knowledge the result of an arbitrary computer program. So the first question is, what does it mean to be a computer program? The decision that we took with Valida is to use this third approach where we define a specialized instruction set on a virtual machine that's it's similar to RISC-V but simplified and optimized for snarks. For example, there's instructions to do finite field operations and a few other tricks to make the circuit smaller than they would be to implement a full, bigger instruction set based on electronic computers for something like RISC-V. So the advantage here is that this is a compromise between doing something that, like using a domain-specific language that outputs circuits directly, and something that works all the way from an ordinary programming language and generates a program. So an important part of this is that we can't just put this out there because we have our own instruction set architecture. An important part of the project is the compiler support that will allow you to compile from LLVM to our virtual machine. These slides are an old version, I'm sorry. But yeah, essentially the position we're taking with Valida is that we want to be the VM that is the most extensible, performant, and developer-friendly. So some of the other VMs out there, there's a whole bunch of them now with daily shifting rankings on how fast everything is. Sorry. Bleh. So most of these have some, but not all components open source. So we want to have everything that you would interact with when working with the Valida VM be fully open source. So for example, not just the prover and verifier, which we of course need, but code around proof aggregation or constraint generation. So both on the far side of the compiler and the writing of the circuits themselves, to the side of compressed proofs and how they're put on chain. We want everything to be fully open, and also with all the rapid development of cryptography in the last few years, we want to be able to switch things out quickly. So the design of Valida building on Plonky3, both of these are designed with a high level of modularity in mind. So how do you build a VM? So you start with the cryptography. We choose the cryptographic system that allows us to have the ideal trade-offs between proof size, proving time, and other desiderata. From there, we develop this specialized instruction set architecture and virtual machine that we design to work very efficiently within that constraint system. So the proving system that we use is Starks. Plonky3 is based on Starks. And then from there, right, we have our instruction set architecture. We have to create compilers that allow you to go from LLVM to this. And then the direction we hope to take this further is to get the best possible performance by adding hardware into the picture, starting with GPUs, maybe one day reaching out to something like ASICs to push the performance even further. And then finally, we want to do formal verification of all of the important software that we have. These last 2 points are a little bit more of a work in progress right now. We have done a lot of what I might say is informal verification, code auditing and benchmarking, but we hope to do everything in an actual theorem prover in the near future. So to optimize to have a really performant ZK VM, there's these sort of two sides of it, right? One side is coming from an ordinary language, is the compiler. The other side is interacting with the cryptography and proof system itself, and the VM sort of sits in between them. So we sort of start at the top and work down, rather than starting with something that we can compile to, like RISC-V. We start with how do we write things that are really optimized specifically for Stark circuits or AIR. And then also, so that this means that when we hit instructions in something like RISC-V, we need a compiler that will translate them to something that avoids the instructions that we don't want to include in the ISA. So a little bit more about our high-level design. We have an ultra-restricted, RISC is what restricted instruction set architecture, modular and ZK friendly. It's divided up into a series of chips. So there's the central processing chip, the memory chip, the arithmetic chip, and then additional things can be added. For example, the range checker. It's a sort of specialized coprocessor. And each of these will be an independent circuit. So we prove traces for them independently and then later make an additional argument to show that they're all compatible with one another. Here's a diagram of the same thing. So right here we have the kind of major parts of the computer, and here's all of the special purpose sort of coprocessors in this one box here. And then we really take design language from the world of actual processors. So we think of these as communicating via buses, where information can flow either read and write or write only. Another note here is that it's a Harvard architecture. So program ROM is a completely separate thing from main memory. This, I think, is a good decision throughout the world of ZK. There's no reason to be able to edit the program code. You know what you're proving when you start. Okay, so I think one of the things in our ISA that makes it a lot more performant than RISC-V is that we eliminated registers. This matters particularly in the setting of the Stark constraint system, more so than it would in something like RISC-V, because or at least a natural choice for designing the circuits would be to have one trace column for each register. So the number of trace columns is a major driver of the cost of proving. So getting rid of trace columns that are for the program registers and just having every piece of data live in memory allows us to make the trace smaller. I think this is probably like the key thing that is driving the performance of our VM. We do have two registers, the program counter and frame pointer. The first tells us where in the memory the next instruction lives. The second says where in memory does the local variables live. We can address RAM in absolute or relative manner. Most instructions use relative addressing, but load and store opcodes use absolute. This is, yeah, I guess I said this, but yeah, there is no stack pointer. So we change a little bit like the low-level calling syntax of functions so that things are constant sized and anything else just goes onto the heap. So this is the high-level design. This is the same for any ZK VM that we first run the original program in with our compiler, generating an execution trace. The prover takes this execution trace and turns it into a cryptographic proof, which can later be consumed by the verifier. Okay, so a couple choices here are the finite field we're using is this 31-bit Mersenne prime field. This is the best field ever because it's essentially just 32-bit arithmetic. Right? You can very easily reduce mod this P with essentially just ordinary 32-bit instructions. So you don't have the sort of high overhead of field emulation that you normally have. Now note that this field is not, is one more than a power of 2, right? So this means that this is still a smooth field. And then, right, because this is small, this is too small to have the right statistical amount of security, so we have to draw challenges from a larger field. But this means that the data that we operate on is all contained in this small field, and only the challenges come from this extension field. This is the unique degree 5 extension of this finite field. It can be generated by a 5th root of 2, but all extensions of the same degree are isomorphic, so that doesn't matter. The polynomial commitment scheme we use is Fry, although this is something that might actually change now that we've had a few improvements to this in the cryptography literature in the past year. So one thing that we're looking at using is basefold. Offers a slightly different polynomial commitment scheme, also based on Reed-Solomon codes, or at least it can be, that can offer a little bit better performance. I'm not going to say anything about the challenger. We use Poseidon. I already listed the chips. Okay, so here, I'll go through this fast because I think this is the same as many other systems that we've talked about. But we separate the execution trace across different chips. We commit to them first, and then we use that value in the hash to get challenges to produce a permutation argument. And this permutation argument, think of the Plonk copy constraint permutation argument, if that's something that's familiar. This is doing something similar, making sure that the I/O that the CPU chip sees with memory is the same as the I/O that the memory chip sees with memory. Okay, then this is turned into cryptography. There's a typo in the second one. This is turned into cryptography by representing these trace column vectors as polynomials, combining them into the constraint equation, and committing and proving that you know the quotient. Again, this is it's the same as every Stark. One note is that all of our constraints have degree at most 3. That helps keeps the constraint, the proving time down, because constraint degree is one of the biggest drivers of proof size and proving time. Here's a little schematic of our compiler setup. I'm probably not going to say a whole lot about this, but one note is that the source is LLVM, so you can compile from your favorite programming language, i.e. Rust, into LLVM, and then this is used to generate optimized code for the Valida VM. I think I mentioned this already. We want everything to be very fully customizable, both in the cryptography and in more application side things, fully open source. And now, do we have this video? Great. So let's switch to that. So this is a little demo of running our VM on just a simple implementation of the Fibonacci sequence.
Hi, this is Morgan Thomas. I'm a cryptographer at Lita, here to demonstrate for you proving on RISC-0 and Valida a performance comparison. So first up here we've got a iterative Fibonacci algorithm written for RISC-0. We're going to compute Fib25, so the 26th element of the Fibonacci sequence, using just this loop here. Let's see RISC-0 proven execution of this program. So this is going to take about 5 seconds, right? So about 1.2 seconds to compile it, and then the rest of the time, more or less, to run it and compute the proof. And look, we've got here 124.54 seconds of user time, i.e. CPU time. Now let's see the same algorithm implemented to run on Valida. This is implemented in C. Now let's compile it to run on Valida and then run it. It's already done. It took 0.27 seconds of user time. It took 0.01 seconds of wall clock time. So this is the comparable number to about 4 seconds for RISC-0 on this example. There you have it.
So yeah, again, here's our punchline. Valida is an extensible, performant, and developer-friendly ZK VM. And we have an early access program for it. So if you're working on something where a VM might be able to help your application, please get in touch with us and use our code, change our code, improve it, and join us. We're hiring across all sorts of of ZK-related engineering. We welcome contributors on our GitHub, and here are our socials. This is the Lita Twitter, and this is Ventali's Telegram. My Telegram didn't make these slides, but if you want to come talk to me.
Thank you, Daniel. We already got questions for you.
Hi. How wide is your opcode? Sorry, just single instruction. Do you still, is it like single field element?
The opcode is a single instruction. The opcode is a single field element, and then there are 5 operands. So each instruction in total would be 6 field elements.
Okay, right. So
which I think is the same as RISC-V. It's the same.
No,
Three are the actual values being computed, and then 2 are binary flags.
Yeah, but RISC-V instruction is 32 bits. Whereas your one is 6 times baby bear. So it's much wider.
Yes, that's right.
Okay. So I guess that means that right, so your ROM is, your maximum ROM size is the size of your baby bear, right?
Right.
Okay. So that's how you avoid not having enough space for, because you cannot do absolute jumps, right? And you cannot do call far away because you cannot address your ROM, right?
Right, so most of the manipulation of memory for things like local variables is done with relative offsets, and those are not very large.
But you can only do relative jumps, right?
No, you can address memory, absolutely, and this would be done with, I think, 4 baby bear elements.
But you just had a sentence in your slides saying that you cannot address ROM.
You cannot, sorry, I misheard you. You cannot address ROM at all.
So you cannot do an absolute jump?
That's right.
Okay, so you can only do relative jumps?
I think that's right, yes.
Okay. So do you plan to have larger virtual memory space or just within a single baby bear?
There's memory is addressed with 4 baby bear elements.
Oh, what about ROM?
I am not sure.
Okay.
Yeah, please do reach out to Ventali to connect more with additional questions. I should say I started recently with Lita, so some of this I'm figuring out too.
And my question is actually probably a build-up on the precedent one. I was wondering, what do you win exactly by treating ROM as something special or not just as a part of memory? I mean, what do you win in performances by preventing from modifying the code of the program first, and then to put it in a completely dedicated, purely isolated memory space?
I think it's really just implementation simplicity. So, right, we're not using actual memory. Right, everything's a metaphor. So it costs nothing to isolate, and not having the program memory just come from a special place makes it a little bit easier to write the circuits. Yeah, it could be done differently. And I think you would just have to do a little bit more work and reason a little bit more about why it's safe. Yes, yes, I think that's right. I don't believe this is the main source of complexity for the compiler. I think things like getting rid of the registers does more. But yeah, we do have a big part of the effort at Lita is to have good compiler tooling. Something that Morgan didn't mention in our video is that this was actually the first time we ran these benchmarks where the compiled Valida assembly resulted in faster proving time than handwritten Valida assembly. So of course this is for a pretty trivial program, and more substantial things might still have a lot of room for improvement in the compiler, but it is up and running, which is something we're very excited about.
Okay, thank you.